quite of insightful keynotes today. Moving forward, we will start with the technical sessions for the symposium. And our first technical session is scheduled at 15:50. And our first presenter is Mr. Nayan. So Mr. Nayan is from Waseda University, and he will be presenting on obstacle overcoming wheelchair, a minimalistic approach. So Nayan, I would request you to carry on with the presentations. The presentation duration is for 15 minutes. After 15 minutes, we'll take question and answers.
My name is Nayan Jyoti Baishya, and I am a PhD student at Waseda University. I'm working on obstacle overcoming wheelchair by a minimalist approach. So as we grow older, our muscles and bones eventually become weaker, resulting us to depend on external assistance. Physical disability may happen because of some mishap as well. In Japan, the percentage of people above age 65 has increased to 26% from 4.9% from 1950 to 2014. And the percentage of people above age 75 has increased to 12.5%. In coming years, this percentage will grow even higher. In another survey in 1996, it was found that out of 3 million disabled people, 1.6 million suffered from motor dysfunction. This situation is not unique to Japan, and it is a matter of global concern. Hence, many researchers have developed assistive technology, such as walking assistive technology, hand assistive technology, and full body exoskeleton as well. One of the assistive technology are related to step climbing wheelchairs. Here are a few of the wheelchairs shown. The first figure shows track-based system, and the second shows articulated leg-based system, and this shows these two figures are hybrid system. The first one is track-based hybrid system, and the second this one is articulated leg-based hybrid system. So although these systems are capable in climbing stairs, these systems have their own shortcomings. For example, track-based systems are slower in plane. Articulated leg-based systems are computationally expensive. Hybrid systems are because there are two systems attached. Those systems are heavy and bulky. So this motivates us to develop a novel climbing mechanism, which mechanism is very simple. So our design inspiration is based on the fact that whenever a person climbs uphill or downhill, we tend to rotate our feet with respect to our ankle joint to maintain the center of gravity, so that to avoid toppling. So I proposed a mechanism where we can rotate this rear wheel with respect to this connecting point, so that the inclination angle can be maintained. So here we can see, if we do not maintain this inclination angle, there will be the inclination angle is very drastically while climbing up and while climbing down. So at first, I was not sure how this mechanism will help in climbing up, but I was pretty much sure that whenever it goes down, if I can maintain the inclination angle, I can save the robot from toppling. So hence, I developed one small prototype and did some experiment. So is the video, can you see the video?
Yes.
Yes, sir.
Okay. So here we can see that if we do not use the control, the robot topples. So we used an IMU sensor to sense the inclination angle, and the robot successfully climbed down. So as I mentioned that I was not sure how it will help while climbing up, I performed the experiment. So without control, we can see that the robot starts slipping and it could not climb up the stairs. However, when I control the inclination angle, the robot slowly climbs up the stairs. later I found out the reason, and through this schematic, I want to explain the reason behind that. Here we can see this figure represents a control system. So we can see that we have maintained the inclination angle, and because of that, the distance between the load and the center of front wheel is less as compared to uncontrolled system, because of which the load share at the front wheel is more in controlled case as compared to uncontrolled case. Hence, the grip, because this downward force is more, the grip on the stairs is more, and hence the slipping can be avoided. So since we were successful in that small prototype, we decided to step up the model to a bigger prototype, a full-scale prototype. So in that, instead of using a rotatory actuator here, we used a linear actuator to maintain the inclination angle. While climbing, the linear actuator extends, and while climbing down, the linear actuator shrinks. So this was the prototype. And here we can see the climbing down experiment. So this robot is powered by a 12-volt external battery and is controlled by wireless remote. There is an IMU sensor mounted on the robot, and which continuously senses the variation in inclination angle, according to which there is a linear actuator which maintains the inclination angle of the body of the robot. So we can see that robot can climb down the stairs. In case of ascending, this is the video for climbing up on the stairs. So slowly, robot can climb up the stairs. So since both this prototype was successful in climbing stairs, we decided to develop a obstacle overcoming wheelchair. So here through this figure, I want to show the problem faced by wheelchair users. So in case of descending through a step, the inclination angle varies drastically. Similarly, while going up, this inclination angle of the chair changes drastically. So this poses as a threat to wheelchair rider. To overcome this, also another problem faced by wheelchair users. So this is a currently state-of-the-art wheelchair. It's called wheelchair. So we can see that the front wheel can easily go over the obstacle, but the rear wheel stuck. To to go over that obstacle, the rider has to come reverse a bit and go with a force. So such kind of force could be harsh for elderly people. So we have developed a wheelchair so that the obstacle can be overcome smoothly. This is the step followed during climbing up on a step. So this system is 5-wheel system where the front wheel and this rear wheel are active rear wheel, whereas this smaller wheel is a passive caster wheel. So whenever the rider approaches obstacle, first this caster wheels are lifted up, and then the front wheel from the force from this front and this active rear wheel, the wheelchair climbs up the stairs, and then once it climbs up the stairs again, this linear actuator extends to engage the caster wheels. Once these caster wheels are engaged, the climbing is done. Similarly, for going down on a step, first these caster wheels are lifted up, and then the front wheel is dropped. Once the front wheel is dropped, the rear wheel is dropped, and once both wheel drops, so again we engage this caster wheels, and that descending process is completed. So through this video, I want to show here we can see this active rear wheel is dropping, and we lift the caster wheels. So because of the force from front and this active rear wheel, we are able to climb up through the obstacle. Similarly, in case of descending through a step, first we lift up these caster wheels. And the first front wheel comes down, and then the rear wheel comes down. Once these two wheels comes down, we again lift up the wheelchair so that the caster wheels can be engaged. And this completes the descending. So in conclusion, we have developed 2 scaled-down prototypes to demonstrate our proposed mechanism for step climbing up and down. And through experiments, we found out that the results were satisfactory. Hence, we decided to develop an obstacle overcoming wheelchairs. And in experiment, we found out that the proposed system can climb up to 35 mm of height. In future, we want to extend the system to develop a step climbing wheelchair. Thank you very much for listening. That's all.
Thank you, Nayan, for that wonderful presentation. So now I would request questions from the audiences one by one. You can raise your hand and they will direct question to the speaker.
Hey, Nayan, this is Shahid.
Yes.
I wanted to ask you one question. What kind of actuators you have used in the wheels to operate the wheels?
These are simple DC motors.
Okay. Okay. Thanks. Thank you for your answer.
Hello, Nayan.
Yes.
I have one question that you have used total 5. There were total 6 sets of wheels, na? So that that one is just that regarding the wheelchair.
Wheelchair.
So that in the middle there were 2 wheels. Can you go to slide? So what was the important for that?
These wheels are caster wheels. These wheels are caster wheels. So because while in plane motion we have to turn. So these wheels it has only 1 degree of freedom. This wheel has it cannot rotate on its what is it, z-axis. So it cannot turn. To take to be able to take turn, these caster wheels are used. These caster wheels are passive wheels.
Okay, understood. I thought it was active. And at the last, you used that BLDC hub motor, no? This one?
Yes.
So actually, okay, it is just one question that are you means how you are able to control it? Means you are doing the velocity control and means what kind of basic control you are giving to this one?
There is a BLDC driver I have used. So just I have put 12 volt supply, and I'm not controlling the velocity.
Okay. Just that simply this accelerometer. Yes. Okay.
Yes.
Okay. Got it. Thank you.
Okay, Mr. Nair, I just have one question. So, as you can see, like the chair is designed. So, what is the like maximum weight it can actually work upon? Like, I mean, maximum weight it can lift through the.
In our experiment, the lady who is using that, her weight is 45 kg. So we have tried up to 45 kg.
So it's designed up to 45 kg, right?
Yes.
Do you think like if it needs to be expanded for a probably if for a like 100 kg weight, the mechanism needs to be redesigned, or this design would work with different actuation?
Okay, this design will work. Only thing is we have to improve the power of motors. We can see that motors were not sleeping. That means the motor's power is not enough. If we increase the power of motors, then same concept can be extended.
Thank you. So
one more question. Means can it climb the stairs also? This one?
No. This right now it can only climb up to 35 mm of height.
Okay.
So we are in future we are planning to extend it to develop a step climbing wheelchair.
Okay. Thank you.
Any more questions from the audience? Okay, thank you, Nayan, for a wonderful presentation. Then,
thank you very much.